I wanted to create a quick video to walk through two of the problems from the written assignment number 6, because students seem to have more trouble with this written assignment than any other written assignment we've had so far. So I want to be sure that everybody's clear on these problems before you move on. Now 2A wasn't so much of an issue, it was more 2B, but I'm going to walk through both of them in this video. And I might even back up to just the explanation next to the problem 2 here. So T is a transformation from the set of polynomials in P2. So these are polynomials with degree 2 or lower, mapped to the set of two-dimensional vectors according to this formula right here. So it's going to take T of a certain polynomial and map it to a vector determined by P of 1 and P prime of 2. So to do 2A, we have to find P of 1 for this, and this should say P of T, I'm sorry about that. So P of 1 for this particular polynomial would be 1 squared minus 3 times 1 plus 7, so negative 2 plus 7, so positive 5 here. And to find P prime of 2, we'd first want to find the derivative in terms of T of this function, remember. We're looking at one specific polynomial that belongs to P2 in problem A here. So the derivative of that polynomial is 2t minus 3, so now we can substitute 2. So we have 2 times 2 minus 3, 4 minus 3, so 1. So when we apply this transformation T to the polynomial t squared minus 3t plus 7, we get the vector, our output is the vector 5, 1. That's what you find in 2A. This vector is your answer. Now, like I said, 2B caused a lot more problems from what I saw. So in 2B, we're trying to find the kernel of that transformation T. And just in general, the kernel of a transformation is the collection of vectors. In this case, and I know that's part of what makes this problem awkward, is the vectors, in quotations here, are polynomials. So in this case, it's the set of all polynomials, I'll call it P, that belong to P2, so they have degree 2 or lower, such that when you do the transformation to the polynomial, you get the 0 vector. So that's what the kernel is. It's the set of vectors that get mapped by a certain transformation to the 0 vector. So in this case, now that the T of P is given by that formula up at the top, P of 1, P prime of 2. And so we want to find when is T of P, so it's given by this formula here, equal to the 0 vector. We want to describe all of the polynomials that get mapped to 0, 0 by this transformation. Okay, now the polynomials in P2 all have the form P of T equals something times T squared. So the only condition to it belonging to P2 is that it has degree 2 or lower. So it's something times T squared, some scalar times T, and then possibly a constant term C. So all the polynomials have this form. Okay, so now matching up one entry at a time. So P of 1 is to equal 0. So P of 1, if we plug 1 into this generic polynomial that I wrote in blue, we'd have A times 1 squared plus B times 1. We're substituting 1 for the T's plus C. So if it belongs to the kernel, then we want A plus B plus C to equal 0. So there's one condition we've come up with for the polynomials in the kernel. Now if I go to the second, let's see, we want P prime of 2 to be 0. Well, again, looking at that generic polynomial that I wrote in blue, the derivative in terms of T would look like this. The 2 would come down, so 2A times T to the first. And then we have B times T, so the derivative would just be that constant B, whatever that is, times 1. And then the derivative of this constant term would be 0, so that would drop off. So the derivative for any just generic 2-degree polynomial here, or degree 2 polynomial, would look like this. Now I can plug in 2. So p prime of 2 is always going to look like this. 2a times 2, substitute that for t, plus b. So 4a plus b, and again, we want this to be mapped to 0, because we want t of this polynomial to be mapped to the 0 vector. So what I would take from that is that b is equal to negative 4a. If it's going to be mapped to the 0 vector, then it looks like b needs to equal negative 4 times a. If I come back to the equation where I left off here in red, I can substitute that negative 4a for the b here. Negative 4a. So that's what's equal to b here. Plus c equals 0. So a minus 4a is negative 3a plus c equals 0. So c is equal to 3a when you move that over. And so now every polynomial in the kernel will look like this. If p is in the kernel of t, then it looks, based on what we have, like p of t has the form a times t squared, b times t, but now we know that b is equal to negative 4a. So negative 4a times t, so here we're replacing the b, and then c is equal to 3a. Well, I could write this as a times t squared minus 4t. I'm just factoring out the a here. But so now we know that the polynomials in the kernel here are going to be just all the scalar multiples of this polynomial right here. So the kernel of t seems to be the span of this polynomial, t squared minus 4t plus 3. If it's in the kernel of t, we have determined that it's some scalar multiple of this polynomial. And so this is the one, this is the q of t that the problem is asking for, this t squared minus 4t plus 3.